Welcome to this webinar on 5 applications where motion control can take you to the next level, presented to you by the Motion Control Association. This webinar will be recorded, and an email with a link to the recording will be sent to you within the next 24 hours. If you have any questions on the presentation material, please feel free to submit questions via the panel on your right, and they will be answered as time permits. You may also contact the speaker directly after the webinar. My name is Kathleen Straight with MCA, and our presenter today is Kristen Lewatsky. Kristen has written about motion control and automation for more than 7 years. As a technology writer, she covers a variety of other subjects ranging from memory and microelectronics to nanotechnology to lasers and photonics. She worked as an engineer on NASA's Chandra X-ray telescope before switching to writing about technology. Her background is in physics and engineering. I also want to thank our sponsor today, Schneider Electric Motion USA. Schneider Electric Motion USA, formerly IMS, manufactures motors and motion control systems. Widely recognized as an integrated motor pioneers, their M-Drive products remain the industry leader with the most complete product offer available. An ever-increasing number of industries and applications are realizing the benefits of integrated motors, including reduced size, cost, and maintenance. Visit their website at www.motion-schneider-electric.com. Kristen, please take it from here.
Okay. Thank you, Kathleen. Appreciate the opportunity, and thanks everybody for being here. And also, thank you to our sponsor who made it all possible. Let's talk about what's going on with motion. What prompted this idea is I talked to a lot of different people in industry, and when I first started out, I was hearing kind of a lot of the same applications, but the last few years, when I'm talking to applications engineers and so on, I'm seeing some more interesting and unusual directions for motion outside the kind of usual suspects. And probably anybody on this call knows what those usual suspects are. You're talking about applications that are very complex. They've got dozens, if not 100 or more axes. You've got very, very synchronized motion. And that's the kind of thing, you're looking at packaging lines, when you're dealing with 300 parts per minute kind of thing. You're dealing with web processes, printing, people who can't type, because that should have said pick and place instead of paper pick and place, but we'll just go with it. Anyway, so those are all the common places, but there are starting to be some other areas. Now, anybody who follows baseball probably heard of something called Moneyball and sabermetrics, which is going on with Billy Beane, and I think the Oakland A's started it. But basically the idea was to exploit market inefficiencies, and that's where you can kind of get ahead a little bit by using motion in your application. So before we go too much further, let's have a quick talk about motion control. And you may have to minimize your little screen in the corner because it looks like you can't see all of my slide deck. But basically, motion control, strictly speaking, closed-loop feedback, generally with servo motors. You can also do closed-loop feedback, obviously, with stepper motors. But depending on how you design the system, stepper motors really do have inherent motion control, in theory anyway. You command a step, you get a step, depending on how tight the resolution is. That can do a lot for you. Now, it also depends on your system design. If you're not careful and you're working with a stepper, you can get lost motion. So obviously, closed-loop feedback is going to get you much closer. But personally, I think that's kind of a squishy area where you can consider a certain amount of stepper activity, even open loop, as being motion control. VFDs, that really depends on who you talk to. I know vendors who would disagree vociferously. I also know vendors who say VFDs are absolutely motion control at a low level. So throw that out there because in some of the applications we're talking about, they were doing variable frequency drives. So again, the thing that prompted this whole discussion is sort of a peripheral example. Fans, for years it was fixed-speed motors, fixed-speed fans, and that worked fine, but it was also spending a ton of energy because it was all or nothing. And somewhere along the line, some bright person got the idea of using variable speed motors on fans, and all of a sudden you started having important benefits coming out of that. You have lower power consumption, increased efficiency, you're wearing your fans out less, so you cut downtime. That means less maintenance. So the spirit of, again, this article is kind of trying to, or not article, webcast is trying to sort of gather up some of the other applications recently that have been getting some of the same economies. One of the key enabling aspects of all of this is that motion control has really evolved in the last 5-10 years, so that a lot of the characteristics that wouldn't have made it appropriate for some of your lower tech, more demanding applications, it's viable. For example, we have connectivity, Ethernet, you've got various concentric motion buses, you've got EtherCAT, Ethernet IP, you've got Profinet, Profibus, Modbus, CANopen. I mean, you can go on, but basically the various flavors act to simplify wiring. They make it easier to update your system. They make troubleshooting and diagnostics much more efficient. It makes it easy, to link into the system. You don't have to climb under a machine or a part to get directly to your component. You can also just plug in anywhere on the network. It enables resilient architectures. If you've got a ring architecture, just because one component fails doesn't mean it takes down the whole system. It also gives you the advantage of shop floor to top floor communications, and that means that you can get advance warning of components that are failing or problems. And obviously, shop floor, top floor speaks of a factory, but if you're using these kind of systems on, an off-road vehicle out there, and it still has connectivity, it's got wireless, suddenly it can be telling you from a very great distance, hey, I've got a problem, come fix me, which is something your dumb components can't do, and that's something motion control can bring to you. And if you're working with an application like mines or drilling or a combine out in the field or something, that's a huge benefit and a big time saver. Another thing that you've got is lots more intelligence in components, and that's been probably a trend for the last decade. I mean, you're getting smarter components, they have onboard processing, they've got memory. So suddenly when you're buying motors and drives, encoders, you've got a lot more functionality involved there. You've got drives that can hand down commands and path planning. You've got encoders that can be daisy chained together, with bits and run one another. Part of what that means is you get more for less. It's easier to install things because a lot of times the parameters you need are already stored in the system. Some of the components will warn you if you're putting something in the wrong way or if you're putting in the wrong component. It's easier, and part of why this is important is, again, if you're somebody in a non-traditional application and you've always said, that motion control stuff, that's too tough for my staff. We don't have training. We don't have the time to deal with it. We don't want to be, running around out there trying to figure out how this stuff works. Let's stick with mechanical. Now you're looking at components that have a lot of capabilities that make it much more user-friendly. And in particular with things like maintenance, it used to be you had the red light. There's a problem. I'm not working. Now you got machines that can give you error codes. They can tell you what the problem is. Very often on the HMI, they can lead the operator through fixing and making any repairs that they need to do. So again, much more user-friendly. Saves time. The shop floor, top floor capabilities can tell you in advance. Again, ease of use. For people who aren't, machine builders whose bread and butter is dealing with motion, that's important, because one of the things to keep in mind is most people out there who are not kind of sweet spot motion players in terms of being integrators or machine builders, your bread and butter is your value proposition. It's not learning how to do motion control. It's doing whatever else you do that brings your customers value. So a lot of these changes that I'm talking about with motion means that it's easier for you to go ahead and adopt it. You don't have to know a ton. You don't have to have deep levels of expertise. And depending on the application, especially when we're talking about some of these, simple things, I'll get to it later, but, an agricultural application, a tractor spreading fertilizer, being able to adjust the level of spreading, that's a single axis. If you've got a smart component, maybe you don't need a controller. Maybe you can just use a smart motor drive, and that makes it easier to put together. That cuts the cost. You've got fewer points of failure. A lot of drives these days are self-tuning, so you don't have people out there, turning pots and trying to get everything up and running the right way. It's stuff that's made to go in quickly so you can focus on what's important to you. And also, there are a lot of components now that integrate safety, and that's another big advantage that it can bring. Let's see. Oh, and another reason, kind of standard, more industrial type applications might be saying, gosh, we can't use motion control. That's those little itsy-bitsy motors that, work on NASA robots and stuff. There are kilowatt class servo motors out there, multiple kilowatts, and they're running dockside cranes, they're running backhoes. You've got all kinds of heavy-duty industrial. There's really a lot of capabilities. So the technology can do much more than you might think. Another thing to keep in mind from a cost point, because it's kind of a high-tech application, it leverages a lot of the advances from the greater embedded community and the greater computational community. So cost actually is lower than you would expect. In a lot of cases, you're getting more functionality in components than in previous years. It's sort of starting to come along for the ride. You can get a controller that can monitor multiple positions. It can give you feedback on current, on speed, and that's something that maybe you wouldn't go out of your way to get as you're designing a machine normally. But if it comes along for the ride and the cost isn't high, start thinking about the kind of things that you can do with that additional information. Capital expenditure versus OpEx is another thing to keep in mind when trying to kind of look at motion control, whether it might work in a non-traditional application. Yeah, it probably is going to cost a little bit more than a fixed-speed motor, but the thing to keep in mind is how everything adds up over the long run. And if you get savings year over year, a lot of these assets last for a decade or more. So, in part, yes, you're having to make the capital investment argument, but long term, you're going to see savings over that. So the idea is to take the big picture view, and you may find that it makes good sense in what you're trying to do. So how do you move ahead and kind of take advantage of these market inefficiencies? That's thinking outside of the box. Look at solving lower tech problems high-tech ways. So one example we can look at is healthcare now. Obviously, healthcare uses a ton of motion for different kinds of medical devices and that sort of thing, but it's starting to get used in really simplistic ways. MRI machines, where you've got the patient table. The patient comes in, they sit down on the table puts them into the MRI, or it runs them through a CAT scanner. And the standard way to do it is use open loop motion. You can use limit switches, proximity sensors. Tells you when you're in the right place, turns it off. The downside is that switches are more components, and they fail. Depending on how they fail and when they fail, you have to keep in mind patient safety is an important factor. So, that's something where motion control can bring you, especially connecting with the connectivity, it can bring you a lot more insight into where that patient table and the patient are at all times. With respect to standard technology, if the patient table stops. Now, some of these tests are very much dependent on the location of the patient within the scanner. Some of them also take a very long time. Some of the MRIs, for example, can take 60 or 90 minutes, and they bring the patient out and in throughout the middle of the test. You need to make sure you're putting that person back in the same place. And if your technology fails, you're going to be in trouble. So one of the things we're looking at doing now is bringing in closed-loop motion. You can run it with a servo motor so that you can be precise. You can include safety if you're using safety components. Absolute encoders let you always know where you are, even if there's a power failure. You can always bring the table exactly back to where it was when you were doing the scan. And again, if you're talking about a 90-minute scan, that makes a big difference. Another thing to look at beyond healthcare, and by the way, with healthcare motion, some of the other things being used are like patient beds, some of the more simple stuff, but if there's a way to do it more safely, to be more resilient against failure, and you're looking at something that's amortized over time, it may be the best solution. Another thing to look at is biotech. Some of the tests that have to be done, just refining the samples for that, can take hours. There's one that's to prepare samples for genetic analysis. You've got to take the fluid, you've got to run a centrifuge, you have to pull off the liquid, add some reagents, run it through centrifuge again, pull off the liquid, add more reagents, and a different mix of reagents. Each time a different mix depending on the particular test you're doing. And this goes on and on and on. If you make any mistakes, you've messed up the test, you have to start again. And you only have a set amount of biological material to work with. So, the old way they did it, they did the centrifuge, they did the test tubes and needles and titration and all that sort of routine, in addition to the problem of just fatigue and making errors and so on. The whole point of a centrifuge is to drive the cells down to the bottom of the test tube so that you can get the liquid out. The problem is if your centrifuge starts and stops too quickly, then you wind up mixing up the cells that you just did all this work to separate out. So it's actually, even though it seems silly to run a centrifuge with motion control, it actually ultimately brings you benefit and saves you time. So now what they're looking at doing is, like I say, using motion control. There was one system that I read about in detail where they've got all kinds of motion in it. They've got stepper motors running this carousel that brings in the test tubes one at a time in order to be aspirated and have reagents added, and then it goes in the centrifuge. It gets run at a certain speed. It gets very tenderly and slowly decelerated, and same thing for acceleration. So they wind up with a better product. They don't have to deal with it. It goes off and does its thing for 60 to 90 minutes. and their samples all ready to go. But at the heart of it is, again, solving a low-tech problem in a high-tech way that gives you better results. It's using motion control to run a centrifuge, which is sort of a variation, if you think about it, on using variable speed fans instead of fixed speed fans, thinking outside the box. Another area now, robotics, I was talking with an analyst who brought this up, and my first thought was, robotics is a motion sweet spot, but in this case, we're not talking about your standard, automotive robots, your scare arms that do these very, very detailed movements. You're really looking at the most low-tech possible solution that can give the functionality you need. One of the key issues that we're up against over the next few decades is the baby boomers are reaching retirement and old age. And all of a sudden you've got a ton of people out there that need care. And at the same time, families are smaller. The younger population is smaller numbers. So they're trying to figure out how they're going to give the care to these people you need. And that's where personal care robotics is starting to be of more interest, because you're not talking about a huge amount of functionality. You're talking about things, robots that can help people get in and out of bed, get in and out of the bath, help them move around the house and reach items on a shelf. I don't know on your screens if you're able to see up in the upper right-hand corner the picture of the guy, but this is a feeding machine that was developed, actually, I believe, by a spinal patient who couldn't use his arms, and he helped develop this, which can cut up food out of a plate, arranged in a certain way, and the patient can use it to put food in their own mouth. Key characteristics these robots have to have. Obviously, safety is huge, which is where your motion components with safety capabilities come in. Definitely it's going to be cost conscious. The thinking seems to be these kinds of robots will be deployed initially at your care facilities, but over time as the costs drop, then they'll start being taken up at home. Again, we've got this aging population, so the key thing is finding ways that motion control can serve these low-end robotics applications and manufacturers to get this stuff out to the market. And there are other things, too, going on with sort of these low-tech robots. I'm sure anybody who watches a little bit of TV has seen the Roomba vacuum and some of these other automatic vacuums, but there's other more high-tech ones that can, clean up and perform security at museums. But one of the interesting applications to me is data centers. It's maintaining the proper temperature and humidity and so on is essential in these systems. And there are these little data center mapping robots, and they have a mast on them, and they tool around and basically measure temperature all the way up and down, map the whole area, and review it constantly. And again, very simple robotics. Was one I read about. It could be programmed to run around the data center. When the power gets low, it goes to its little docking station, it plugs itself in, it gets charged, and then it leaves and goes out about its business. And in the meantime, it's wirelessly connected, so it's constantly transmitting data. IBM has another one that looks a little bit more like a rolling bread rack, but it's the same kind of thing. They're just festooned with sensors. It's really very cool. But the key thing, I was talking with Michelle Figgs at IHS about some of these apps, and her thing was, it's got to be, there's got to be the ease of use out there, and not just for putting in the technology, but also being able to program it. That's a key part of the usability here. You don't want to have some of these designers who are used to doing pretty simple applications having to go to a lot of effort to learn how to program a PLC or whatever. You want to make it easy for people. So that's kind of the responsibility of the motion industry. A lot of that is underway already. And that is, again, going to make it easier going forward to move into some of these non-traditional areas. And for those of you out there who are trying to figure out how to apply it to what you do, it's going to make it more user-friendly to you. Another one is materials, well, not materials processing, materials transport. Now, one thing that I came across was conveyors. And kind of the basics of conveyors, you talk to a lot of people who say, conveyor is constant torque application. And for fixed load, yes, it's true. Now, I've seen analysis that shows that even, and by the way, what I mean by constant torque is that if you change the speed, you're basically still going to be consuming about the same amount of power because, once it's rolling, it's rolling. Now, I've seen analysis that shows that, yeah, you can get a certain amount of savings going to variable speed, but it's a couple grand a month over the course of 10 years. Maybe it's going to be a couple $100 grand, but guess what? Your variable speed drive costs about that same amount, so it zeroes out. You've got something that's, a little higher tech and maybe less familiar to your gang. So, you don't necessarily have that be a value proposition. And that may add up that way depending on the prices and also depending on having that fixed load. The thing is you don't always have fixed load. Some applications have quite a variable load. One of the things that I heard about talking to an analyst is a conveyor system going from a coal mine to a depot, I believe, or a processing center, a long way away. Now, if you've done any looking into some of the natural resource mining, these conveyor belts are enormous. There's one so large it can be seen from space. It's in, I want to say Morocco, and it's about 100 kilometers. It's a series of conveyors, but and there's another one. I think the record for the longest conveyor at present is India, and that's something along the lines of 70 or 80 kilometers. So it's actually quite feasible that in some of these cases, the weather conditions at the mine are going to be very different from the conditions on the other end. Now, in a lot of cases, the ore is covered up to protect it. So if you've got rain at one end, it's not like it's going to get soaked the whole way. But guess what? If you're pulling coal out of an open pit mine or some other ore and it's getting soaking wet while it's coming out, all of a sudden you're putting a lot more weight on your conveyor, and that can cause things to lug. That can even cause damage. It can cause failure, and so on. So in one case, what they wound up doing was instead of going with a fixed speed motor, they put sensors out closer to the mine and added a controller. You can do variable speed motion or even motion control, and poof, you're putting less stress on your motor. You're getting the material to where you want it to be in time. You're avoiding downtime, which in a case like that, and you think about it, if you got downtime with a 24/7 operation and your material stretched out tens of kilometers, that's a pretty big deal. There are plenty of other conveyor applications that can benefit from motion as well. In factory floors, I mean, again, you think conveyors, you think fixed speed, but if they're trying to interface with other machines, you may need the adjustability. In particular, if you've got a conveyor that has to do a certain amount of acceleration, deceleration, that's where motion control can actually make a big difference. And it can be as simple as preventing your product from falling over, tipping over without, by not doing a hard stop-start. You can make sure that you're maintaining product orientation for inspection so that if it's going around a turn or whatever, it's not doing it so quickly that it's spilling over your product. In general, if you're looking at short distances on this, you probably talked about stepper motors. Longer distances, that's going to be more like servo motors. And another place that motion control on conveyors is important, and this really probably falls more under the heading of kind of standard applications, would be some of your very position-sensitive inspection applications, where again you want to make sure that you're getting your product or your inspection component not just in the right orientation, but in the right position, and that you're able to track it the whole way. That said, I was talking to an analyst last week or the week before on this topic, and he actually knew a beverage manufacturer that wholesale through their entire line swapped out their standard motors for AC permanent magnet, basically permanent magnet servo motors. I believe they were still running them open loop, but they got so much cost saving out of running them with the permanent magnet motors that they made the change anyway. So, conveyors, it's worth taking a look at your operation. It's worth taking a look at your requirements and see whether some of these motion technologies might just be a better fit for you. Pumps. Now, this is very interesting. You got pumps all over the place in everything from chemical processing, a lot of process industries. We've also got it in heavy industry like mining, oil drilling. Probably most of you have heard of something called mud in oil and mining, which is not what it sounds like. It's actually a fluid that gets used for specific purposes. And it gets pumped. They usually do the standard operation. Fixed speed motor runs the pump full out, and then you've got a valve that you use to shut down the flow or shut it off completely, depending on what you need. Shutting it off completely is known as deadheading, and that can actually be kind of a big problem. What happens with deadheading is you shut off the valve, you got your pump going pell-mell. So all you're doing now is just circulating all of that fluid over and over again. Circulating it creates friction, and that is going to start raising your temperature, and it also creates more wear on your pump. It also puts pressure on your valve. Now, in the best case scenario, that neither of those are good. Eventually, you're going to run into failure if you impose too much wear on your components. But where it really becomes a problem, again, with things like mining and oil is that it's very important to not have water contamination in that mud. Because what happens is if you deadhead and you suddenly get a whole lot more pressure, remember thermodynamics, you add more pressure, guess what? Your temperature goes up. And if your temperature goes up too high, your water turns to steam. Your water turns to steam, you suddenly get catastrophic expansion, and you're potentially looking at blowing apart your pump housing, which is not good, especially in the process industry. A lot of those applications run, full out 24/7. And the last thing you want to do is blow up your pump. Not only are you stopping operations, you're potentially having to clean up a mess. You're going to be down dead in the water, so to speak, pardon the pun, until you can get somebody out to fix it. It's a mess. So a thing that they're looking at doing now is instead using motion control to vary the pump speed. So instead of having it be an all or nothing thing where you're either running or you're deadheading, they're actually using motion control to slow down the flow the fluid flow, so that when it comes time to shut things off of the valve, there's not a huge amount of pressure. It's not an all or nothing. It's not super sudden. And that doesn't rule out the need for valves. You're going to need valves, but you're doing it in a way that's much easier on the system. You're more efficient. You're not burning energy for no reason. You're also removing points of failure. You're reducing the prospect of downtime, expensive maintenance. So it kind of all comes together to be really beneficial. Another interesting thing, and by the way, I sort of early on in doing this lost track of the whole 5 applications kind of thing, because things really did seem to go out much more broadly than I initially just figured I could scare up 5 items, but there's a fair amount going on here. So, and one of the interesting things that I found out about is kind of some work going on with hydraulics. The standard wrap with motion control, especially with some of these kilowatt class servo motors that are out there, is they can come in, they can take over from pneumatics and hydraulics and get the job done. Even with kilowatt class, there are applications that are probably too much for servo motors, certainly, but there's kind of a hybrid thing going on out there that's pretty interesting. It's electrohydrostatic actuators. Before we talk about those, let's kind of go through the basics of hydraulics. In a hydraulic system, you've got a master cylinder, and it's connected by lines to your one or more slave cylinders. You use a compressor / pump to drive the non-compressible hydraulic fluid in your master cylinder. That transfers force through your hydraulic lines, and you can generate a huge amount of force by the economies of the scale of the sizes of the different cylinders. So that's a good side, and it works tremendously for a lot of heavy industry, but the problem is it's not terribly efficient. The seals and the hydraulic lines leak. If you're trying to do an application like subsea drilling, you have got to get hydraulic lines that go all the way from your pump compressor to your actuator. That's a long way, which means a lot of money. That means things that can fail. So it's a good technology, but it's got its problems. Now, electrohydrostatic actuators, the technology was actually first developed for airplanes and aerospace. And the idea was to come up with a better solution. Couldn't, at that point, get what they needed out of purely electrical solutions. So what they did was used electrical technology to bring the pump part of the hydraulics closer to the hydraulic actuator. So instead of having your master cylinder off-site and running the hydraulic fluid through lines, they actually put an electric pump right at the actuator. And it winds up going all in a single package. That gives you an electrical interface, not a fluid interface. So it's much more controllable. It's cleaner, it's energy efficient. You don't wind up, you're able to be much more accurate with your motion. And it's also, surprisingly, it can be much more cost effective, because the thing is, it's easy for people to look at a hydraulic cylinder and say, gosh, that's probably cheaper than motion. But that's not all that you put into a hydraulic system. I mean, think about it. You've got to have that compressor, you've got to have the pump, you've got to have the lines, which can really add up. You've got to have the fluid that's got to go through all of those lines. You've got to have, they take a lot of maintenance. You've got to do the maintenance. You've got to pay to run that compressor all the time. So it actually adds up. And when I was speaking with one of the analysts about this, he really was speculating that this is a direction that could be applied to a lot of industrial areas. And there are a couple of companies out there that are starting to look at this as an industrial commercial product. So my guess is that this is kind of an area to keep an eye on, and if you're currently using hydraulics, it's something that's worth investigating to see whether this might be a solution that can get you some more reliability, cut some costs for you, and also simplify maintenance. So another area where there's some interesting stuff going on is off-road. And this encompasses a lot of things. I don't think we're going to have time to go into all of it. But certainly agriculture, a lot going on there. You know, standard way to do it used to be get in the vehicle and drive and do whatever you needed to do. And if you were spreading fertilizer or whatever, you basically flip the switch on the hopper and just kind of let it go and hope that you could be consistent about what you were doing and broadcast evenly. But, you know, human nature is human nature, and it's not as easy to do as you would think. Well, they are starting, some of your tractor heavy equipment manufacturers are starting to put in GPS capabilities that are tied to motion so that these vehicles can go exactly where they're supposed to. You also have the option of adjusting the broadcast speed or tying it to the speed of the vehicle. So that's stuff where, yeah, sure, you can do it with the old technology, and you'll probably do okay. But in a case, you know, especially with your fertilizing plants, you don't want to get too much, you don't want to get too little, and this is a case where it becomes much less labor-intensive, it becomes much less subject to the skill and attention span of your operator because now you've got it automated. So again, there's an old way to do it. Sure, you can do just fine, but if you're making one of these systems, you might just find that looking at motion as an option could get you some better capabilities to deliver to your customers. Construction, same thing. Backhoes, cranes, that sort of thing. You can use motion technology. There are things like characteristic, you know, you're digging a hole, and if you have to reposition and come back, you want to know where you are. And certainly you can do that with GPS. You can do that with a bunch of pretty costly technology, but you can also do it with feedback and motion. So again, it's not solving problems that can't be solved any other way, but what it's doing is throwing out opportunities to solve problems in a way that may be more cost-effective when considered as a whole package. And some other, let me throw this back here, some other things that I didn't want to quite go into the gory details on, but CNC, that's a pretty obvious motion application, but increasingly some of your spindle apps are starting to be better fits for motion. There are additional heavy industry type applications, steel manufacturing, rubber. There's, I guess the thing that I came away with talking to people about all this is just really take a look at the technology and take a look at some of the new options out there, because you may be able to find market inefficiencies that you can exploit if you look at the technology, or process inefficiencies might be a better way of putting it. Now, this gets tricky. One of the things I was asking the analysts about is if there are savings involved, why is it hard to get end users to think about it? But one of the things that you might be up against is you're trying to get approval for capital expenditure when the savings are going to come to the people who are running facilities, and maybe it's a completely different business unit or a different department or whatever. So it's really important to kind of take the whole picture view, look at the value, look at what you can get. In a lot of cases, machine builders are looking to put out a machine at the lowest possible price. So they want to go with the technology that's going to have the lowest capital expenditure, but long term, you've got operational expenditures, and that's really where, as end users, you need to take a look at the big picture for you and potentially push your machine builder or your OEM to consider some of these other options, even if that's not going to give them exactly the numbers they want. Ultimately, it's going to be the best bet for you. So I think I've pretty much run through all the points that I wanted to do. Basically, the upshot is, number one, the technology, explore it because you might be surprised. The entry is not nearly as difficult as it once was. There's a lot of work, even on the programming side. A lot of the companies out there that are supplying things now have controls, libraries, things designed to make it easy for you to integrate, easy for you to program. So it's not nearly as difficult to put together a system, and especially in many of these applications, you're really talking about only a couple of axes. You're not talking about doing highly synchronized control. The exploit market inefficiencies, obviously, again, you want to be looking for places where you've got savings. Take the long view, price the whole system. Look at the big picture because that's where the savings are, and that's where you can potentially get ahead of your competition by, doing the Billy Bean thing. Take a non-traditional view and see where it's going to get you. Let's see, I think we are at the end of our time, so I don't know that we have time for questions. Kathleen, I'll leave that to you. Anybody wants to get in touch with me, my contact information is up there, so feel free to email or phone, and I'm certainly happy anything I can answer to make sure that I get it taken care of.
Great. Thank you, Kristen. It looks like we don't have any questions at this time, but again, if you do have questions for Kristen, feel free to get in touch with her. Thank you for this informative webinar and to all the participants today. And I especially want to thank our sponsor, Schneider Electric Motion USA. Be sure to check out all the other webinars that we have available. They're listed on our website, www.motioncontrolonline.org. And then as a reminder, the webinar has been recorded and an email with a link to the recording will be sent to you very shortly. Thanks again, everyone. Thank you, Schneider Electric Motion USA. Have a great day. Thank you.